So how should this particle of O collide with the particle of N2O to result in a successful reaction? So what I'm focusing on step 2 is the newly formed bond. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 5.4 to 5.7. As you can see on this slide, these topics fall under Unit 5 in the AP Chemistry curriculum, Kinetics. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now, let's move on to the review for Topic 5.4, Elementary Reactions, and Topic 5.7, Introduction to Reaction Mechanisms. I have decided to combine these two topics together because their essential knowledge statements are very similar to each other. Here are some essential knowledge statements from the AP Chemistry course and exam description. For Topic 5.4, we have the rate law of an elementary reaction can be inferred from the stoichiometry of the particles participating in a collision. And elementary reactions involving the simultaneous collision of 3 or more particles are rare. And now for Topic 5.7, a reaction mechanism consists of a series of elementary reactions or steps that occur in sequence. The components may include reactants, intermediates, products, and catalysts. And the elementary steps, when combined, should align with the overall balanced equation of a chemical reaction. A reaction intermediate is produced by some elementary steps and consumed by others, such that it is present only while a reaction is occurring. And experimental detection of a reaction intermediate is a common way to build evidence in support of one reaction mechanism over an alternative mechanism. Now let's move on to the practice for topics 5.4 and 5.7. This is question 1. In question 1, it says, a proposed mechanism for a chemical reaction is shown above. Answer the following questions related to this mechanism. In part A, it says, write the rate law for elementary step number 1. And in topic 5.4, elementary reactions, one of the essential knowledge statements says that the rate law of an elementary reaction can be inferred from the stoichiometry of the particles participating in a collision. So what exactly does that mean? Well, if we have one particle colliding as a reactant, then the reaction would be first order with respect to that particle for the rate law for that elementary step. And if we happen to have 2 of the same particles colliding as reactants in an elementary step, then the reaction would be second order with respect to that substance. But looking at step 1 and step 2, I don't see any substances that are listed twice as reactants in the same elementary step. So it looks like it's going to be first order with respect to each substance because there's only one particle of that substance as a reactant. So as we see the example for part A and part B, I think you'll begin to understand that the stoichiometry refers to the number of the particles, and then that would be the order. So for elementary step number 1, I see one particle of substance A colliding with one particle of substance D2Q. So in my rate law, it's going to be first order with respect to A and first order with respect to D2Q. So there's my rate law. Rate equals K, the rate constant, times the concentration of A times the concentration of D2Q. So again, first order with respect to each substance because there's only one of each particle. Now we have a very similar process for part B of question 1, which says write the rate law for elementary step number 2. So again, first order with respect to substance AQ and first order with respect to substance D2Q because we have one particle of each colliding as reactants in this elementary step. So rate equals the rate constant K times the concentration of AQ times the concentration of D2Q. Again, first order with respect to each substance. Now, if you are given a proposed mechanism on the AP Chemistry exam and you need to come up with the balanced equation for the overall reaction, all you need to do is simply add the steps together. But you should pay attention to any substance that appears as a reactant in one step and then appears as a product in another step. So before I add step 1 and step 2 of this proposed mechanism together, I'm going to look for any substances that would appear on opposite sides of the equation, and I will cross them off. So for example, substance A appears as a reactant in step 1, and then substance A also appears as a product in step 2. So I'm going to cross off substance A on opposite sides of the equation. And then in a similar fashion, I see that substance AQ appears as a reactant in step 2, and it also appears as a product in step 1. So again, I'm going to cross off that substance that appears on opposite sides of the equation. So my answer to part C of question 1, the balanced equation for the overall reaction, would look like this. So on the reactant side of our balanced equation, we have 2D2Q. And then on the product side of our balanced equation, we have 2D2 plus Q2. So there is our answer to part C. That's the balanced equation for the overall reaction for this mechanism. And again, when I was adding step 1 and step 2 together, I crossed off substance A on opposite sides of the equation, and I also crossed off substance AQ on opposite sides of the equation. And we should know an important difference, which is coming up in part D of this question. And that important difference is, what is the difference between a substance that behaves as a catalyst versus a substance that behaves as an intermediate? So they are similar, but they are very different. What makes them similar is that you can cross off these substances on opposite sides of the equation, but there is a very important difference between something that is consumed and then regenerated versus something that is produced and then later consumed. I'm going to start with the intermediate because that's actually listed explicitly in one of the essential knowledge statements for topic 5.7. This is what it says about a reaction intermediate. It says it is produced and then consumed. So it is first produced and then consumed. So substance AQ in our mechanism, it appears as a product in step 1. So first it's produced and then it is consumed as a reactant in step 2. So substance AQ, first produced and then consumed, that would be classified as an intermediate in this mechanism. And then what about substance A? Well, it is first consumed as a reactant in step 1, and then it is regenerated in a later step, in step 2. So substance A is a catalyst, first consumed, and then later produced or regenerated, whereas substance AQ is an intermediate, first produced, and then later consumed. That's an important distinction that you should make, especially if you see a mechanism question on the AP Chemistry exam. Okay, well, let's see if you understand the difference between a substance that behaves as a catalyst and a substance that behaves as an intermediate as we apply your knowledge of that important concept to a new mechanism. So this is question 2. It says a proposed mechanism for a chemical reaction is shown above, and a student claims that the H3O plus ion behaves as an intermediate in this reaction because it appears as both a product and as a reactant in the proposed mechanism. Do you agree or disagree with the student's claim? Justify your answer based on the mechanism. So back in question 1, we discovered that a substance that is first consumed and then regenerated would behave as a catalyst, whereas a substance that is first produced and then later consumed would behave as an intermediate. Let's go find the H3O plus ion in this mechanism. Well, the first time I see the H3O plus ion in step 1, it appears as a reactant, and then I see it again as a product in step 2. So first consumed and then later regenerated, that would make the H3O plus ion, or the hydronium ion, that would make it behave as a catalyst. So my answer to question 2 is the following. I disagree with the student's claim that it behaves as an intermediate. It's actually a catalyst. And so why is that? Because the hydronium ion, H3O plus, is consumed in step 1 and regenerated in step 2. So therefore it behaves as a catalyst in this reaction. Now what I did is I took this particular mechanism that I had found on the 2025 AP Chemistry Free Response section. This was question 7, part C, from the 2025 free response questions, and I just rewrote that question slightly different in terms of the student makes the claim that it was an intermediate. So we are correct that it's a catalyst, and that's why I said I disagree with the student's claim. But now I'll show you what that original question looked like on the 2025 AP Chemistry free response section. So it said, glycolic acid can be produced from the hydrolysis of methyl glycolate. A proposed mechanism for the reaction is given. And it said, a little bit different than the way I asked it in this packet, it said a student claims that the H3O plus is a catalyst. Do you agree or disagree? And the official answer is yes. I would agree that it is a catalyst because it is consumed in step 1 and regenerated in step 2. Now, one important reason why I brought up this example of a question from the 2025 AP Chemistry exam is I'd like to show you examples of incorrect student responses because it's my hope that I can give you advice to help you avoid common mistakes. So in my next lesson for AP Chemistry Review and Practice, I'll talk more about topics 5.8 through 5.11, and as you can see on this slide, topic 5.11 is all about the role of a catalyst. So it's entitled catalysis. And so what did students do on the 2025 AP Chemistry exam when they answered question 7, part C? They didn't read the question carefully. And what they did was they told us all about what a catalyst does in general, such as it speeds up the reaction or it lowers the activation energy, but they didn't talk specifically about what it was doing in the mechanism that was given to them. So the correct answer to question 7, part C from the 2025 AP Chemistry exam is that yes, it is a catalyst. The hydronium ion, or H3O plus, is consumed as a reactant in the first step and then is produced as a product in the second step. That was the important detail from the mechanism. So always read the question carefully and make sure you're answering the question that is being asked. So is it true that a catalyst does speed up the reaction or lower the activation energy? Yes, but that wasn't the essential component of the mechanism. So consumed as a reactant and then produced as a product, that was the important detail. Now, some students did the following. They said it's not a catalyst. They said it was a spectator ion because it was crossed off on both sides, so that's incorrect. Again, they gave us statements that although they were true, were simply defining what a catalyst does to affect the overall reaction, but they didn't talk about the specific details of the proposed mechanism. So I'm just showing you that it's very important to read the question carefully, make sure you're answering the question that's being asked, and hopefully at this point in the lesson, you're very clear on the difference between an intermediate, which would be first produced and then consumed, as opposed to a catalyst, which is first consumed and then produced. So if you give a very vague statement about it appears on both sides of the reaction or as a product and a reactant, that's not specific to the role of a catalyst in this mechanism. All right, before we take a look at question 3 in this packet, there was another question that I found from the 2021 AP Chemistry free response questions. Again, just an example of what to do carefully when you're answering a free response question. So this was question 1, part G, from the 2021 AP Chemistry free response question. And it said, after the reaction has proceeded for several minutes, it was in the presence of a catalyst. The question was, does the amount of catalyst increase, decrease, or remain the same? Justify your answer. So again, if a catalyst is first consumed and then regenerated, I would think that the amount of catalyst would remain fairly constant. And so that was the intended answer to question 1, part G, from the 2021 AP Chemistry free response questions, that it would remain the same because in a catalyzed reaction, the net amount of catalyst is constant. Again, it's going to be consumed and then regenerated, and that would keep that amount fairly constant. So what did students do incorrectly? Instead of talking about the amount of catalyst remaining fairly constant, they would say things such as, it speeds up the reaction. So again, they're discussing the effect of a catalyst, but not focusing on that conservation of the material. Or they would say things such as, a catalyst is not involved in the reaction, or it does not react. So they had to focus on the net amount of catalyst. Again, that was from the 2021 AP Chemistry exam, and that was question 1, part G. Now, what I will do when I mention these types of examples is I will put in the video description area all of the official questions and scoring guidelines to any of these AP Chemistry questions that I'm mentioning from such as 2025 or 2021. So you'll see all of those links in the video description area. All right, now let's go ahead and return to the specific question from this packet. This is question 3. In question 3, it says, a two-step reaction mechanism is proposed for a chemical reaction as represented above, but you'll notice that step 2 is blank for the moment. So that takes us to part A of question 3, which says, based on the given information, so we have step 1, and we have the equation for the overall reaction, write the balanced equation for step 2 of this mechanism. So can we fill in the missing details and write the equation for step 2? Well, if I look at the overall reaction, I see 2 molecules of NO2Cl as a reactant, but there's only 1 molecule of NO2Cl in step 1, so I'm going to add another molecule of NO2Cl as a reactant in step 2. And now on the other side of the equation, on the product side and the overall reaction, I see 2 molecules of NO2 on the product side and the overall reaction. So again, there's only 1 molecule of NO2 in step 1 on the product side. So I'm going to add another molecule of NO2 on the product side for step 2. Now, what about the Cl2, which is featured as a product in the overall reaction? Well, I'm going to go ahead and add Cl2 as a product in step 2. And now you'll notice that there's 2 Cl atoms on the right in step 2, but there's only 1 atom of Cl on the left in step 2. So we have to add another Cl, and this is how I will do that. So I'm going to add a single Cl as a reactant in step 2. So now that is complete. That takes care of step 2. So that is the answer to question 3, part A. Now here's the follow-up question. Now that this 2-step mechanism is complete, it says, does the substance Cl in this two-step mechanism behave as a catalyst or as an intermediate? Well, the answer is it would be an intermediate. And the reason why is because the Cl is produced in step 1 and then consumed in step 2. So therefore, the Cl behaves as an intermediate in this reaction. And now let's go ahead and take a look at question 4, which is a companion to question 3. They're very similar in that we're looking at Cl on opposite sides of the equations. Now let's go ahead and move on to question 4, and you'll see something a little different for the substance Cl. So this is question 4, and now instead of coming up with one of the steps, all we have to do is write the overall equation, the balanced equation for the overall reaction. So I'm going to cross off the Cl, which appears on the left in step 1 and on the right in step 2. So based on the given information, write the balanced equation for the overall reaction. So I'll cross off the Cl on the left and the Cl on the right. And then I will also cross off another substance that appears on both the left and the right, and that is the ClO. Now, what do I have left? Well, I have 2 molecules of O3 on the reactant side, and I have a total of 3 molecules of O2 on the product side. So here's my answer to question 4, part A. 2O3 as the reactant and 3O2 as the product. That is my answer to question 4, part A. That's the balanced equation for the overall reaction. Now, remember that in question 3, the chlorine behaved as an intermediate because it was produced in step 1 and consumed in step 2. Now let's take a look at what's happening in question 4. It says, does the substance Cl behave as a catalyst or as an intermediate? So now the Cl is actually first consumed and then produced. So the answer to question 4, part B, that the Cl is actually consumed in step 1 and then regenerated in step 2. Therefore, the Cl behaves as a catalyst in this reaction. So that's the answer to question 4. All right, there's one more question that would be relating to mechanisms and elementary steps. So this is question 5. In question 5, it says, which of these 3 equations, we have equation 1, equation 2, equation 3, which is least likely to represent a chemical reaction that occurs in a single elementary step? Justify your answer in terms of particle collisions. You may remember that I had mentioned one of the essential knowledge statements for topic 5.4, and it was about the simultaneous collision of 3 or more particles. So you can see that elementary reactions are supposed to occur in a single step involving particle collisions, but elementary reactions involving the simultaneous collision of 3 or more particles would be very rare events, so not likely to occur. So the correct answer to question 5 is that the equation that represents a chemical reaction that would be least likely to occur in a single elementary step would be equation 3. So I said equation 3 is least likely to represent a chemical reaction that occurs in a single elementary step because the simultaneous collision of 3 particles is a rare event and not likely to occur. So hopefully these example questions were helpful for topics 5.4 and 5.7. I just wanted to mention that we still have more things to consider about reaction mechanisms in the next lesson for AP Chemistry Review and Practice. I'll talk about topic 5.8, reaction mechanism and rate law. All right, now it's time to move on to the review for topic 5.5, collision model. Here are some essential knowledge statements from the AP Chemistry course and exam description. For an elementary reaction to successfully produce products, reactants must successfully collide to initiate bond-breaking and bond-making events. In most reactions, only a small fraction of the collisions leads to a reaction. Successful collisions have both sufficient energy to overcome the activation energy requirements and orientations that allow the bonds to rearrange in the required manner. And the Maxwell-Boltzmann distribution curve describes the distribution of particle energies. This distribution can be used to gain a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction, and also how that fraction depends on temperature. And now it's time to move on to the practice for topic 5.5. This is question 6. Question 6 says, the rate law for the reaction represented by the equation above is rate equals K times the concentration of A times the concentration of B. So this rate law tells us that the reaction is first order with respect to A and first order with respect to B. It says the initial reaction conditions for 3 trials are listed in the following table. Part A of question 6 says, when comparing trial 2 to trial 1, which of the following are true? Check all that apply. So we have to consider the frequency of the collisions, the value of the rate constant, and the activation energy as we change from trial 1. I can see 1 molar for concentration of A, 1 molar for concentration of B, and a temperature of 25 degrees Celsius. So what happened in trial 2 is that they doubled the initial concentration of both A and B. So with a higher initial concentration of the reactants, does that change the frequency of the collisions between the particles? Yes. With a higher concentration of reactants, we would expect there to be a higher frequency of collisions between particles A and B. Now, what about the value of the rate constant K? Will that be affected when we double the initial concentrations of the reactants A and B? So in an earlier lesson in AP Chemistry Review and Practice, I talked about topic 5.2, Introduction to Rate Law. And you can see highlighted on this slide, one of the essential knowledge statements from topic 5.2 says that the proportionality constant in the rate law, which is known as the rate constant, the value of this constant is temperature dependent. The value of this constant is temperature dependent. So when we went from trial 1 to trial 2, did we change the temperature? And the answer is no. So the rate constant K remains the same going from trial 1 to trial 2 because the temperature remains constant. So I'm not going to check either of these statements. The value of the rate constant K will not decrease, it will not increase, it remains the same because the temperature remains constant. And now, what about the activation energy? Will that be affected? Well, although this lesson does not include topic 5.11, that will be for my next lesson on AP Chemistry Review and Practice, I just highlighted that if you do have a catalyst that can provide a reaction path with a lower activation energy. And there's no mention of a catalyst in trial 1 or trial 2, so in the absence of a catalyst, we can assume that the activation energy for this reaction remains the same. So I'm not going to check either of those statements. The activation energy will not decrease or increase. It will remain the same. Now let's go ahead and take a look at what happens in trial 3. Let's move on to question 6, part B. It says, when comparing trial 3 to trial 1, now we're not changing the initial concentration of the reactants. They remain at 1 molar, but what we are changing is the initial temperature from 25 degrees Celsius to 50 degrees Celsius. So we have the same initial concentration of the reactants, but a higher initial temperature. Let's focus on the frequency of the collisions. Higher temperature, greater average kinetic energy, so the particles are traveling at a faster speed. They should collide more often, and they should also collide with more force, with more energy. So the frequency of the collisions between particles A and B will increase because higher temperature, greater average kinetic energy, so more frequent collisions between the particles. Now, what about the value of the rate constant? Remember that the rate constant is a temperature-dependent value. So if you increase the temperature, then yes, you will also increase the value of the rate constant K. So the rate constant K will increase because the temperature is increased and the value of K is temperature-dependent. What about the activation energy? Again, that would only typically occur in the presence of a catalyst. Would you have a path with a lower activation energy? We're not talking about a catalyst in trial 3, so the activation energy remains the same. All right, so those are the answers to parts A and B of question 6. Now let's take a look at question 7. In question 7, we are given a chemical equation, and it says carbon tetrachloride can be synthesized according to the reaction represented above. A chemist runs the reaction at constant temperature at 120 degrees Celsius in a rigid container. Now, at 30 degrees Celsius, the rate of the reaction is very slow, and no reaction is observed to occur. However, at 120 degrees Celsius, the reaction occurs at an observable rate. So here comes the question about a difference in temperature and the reaction rate, and that is part A. Explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. So we're looking at the difference between 30 degrees Celsius, so very slow rate, and 120 degrees Celsius, much faster, more observable rate. So in topic 5.5, one of the essential knowledge statements talks about energy and talks about the activation energy requirements. So this is what it says. In most reactions, only a small fraction of the collisions leads to a reaction. So successful collisions have both sufficient energy to overcome the activation energy requirements, along with orientations that allow the bonds to rearrange in the required manner. Let's focus on the energy to overcome the activation energy requirements. Now, this particular question that we're looking at in this episode of AP Chemistry Review and Practice, it's another example of something that I found from an earlier AP Chemistry exam. So as you can see, this is from the 2017 AP Chemistry free response questions, and this was question 1, part B. Again, I will put the link to the official questions and scoring guidelines in the video description area. And so this is what the official scoring guidelines said. Explain how the higher temperature, so 120 degrees Celsius, affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. So this is what they said. At the higher temperature, the particles have greater average kinetic energy than at the lower temperature. And so why would a higher temperature be associated with a faster rate? Well, there are more collisions with sufficient energy to overcome the activation energy. Now, let's take a look at what students did potentially incorrectly on this question. So you can see on the right side of this slide, responses that demonstrate understanding. So higher temperature, greater average kinetic energy, more collisions with sufficient force between the particles with greater kinetic energy, more energy to overcome the activation energy, and more collisions. So what did students do that was incorrect? Failure to answer the prompt. So again, read the question carefully and pay attention to what they're looking for. The students did not talk about how an increase in temperature affects the collisions between the particles. Or they simply said more collisions without talking about more energetic particles. Not enough use of the word more as a comparative word. And then some students believed that, well, it's only until 120 degrees that collisions occur. So they thought that no collisions occur until 120 degrees Celsius is reached. Or they thought that somehow there was a catalyst, maybe thinking that temperature is actually behaving as a catalyst, which is incorrect. Some students focused on either the energy or the frequency of collisions, but not both. Now, the next part of this question involves drawing a curve. It says the graph below shows a distribution for the collision energies, and this is at 120 degrees Celsius. So what you have to do is draw a second curve on this graph that shows the distribution for the collision energies at 30 degrees Celsius. You will also see, in addition to the curve, you'll see a vertical line that has been labeled as the activation energy. So we have energy of collisions on the x-axis, and we have the fraction of collisions on the y-axis. So you have to draw the curve at 30 degrees Celsius, and there's specific features of this curve that we're looking for. Now, in my video that includes topic 5.5, which again, I'll put a link to that video in the video description area. This is from my YouTube playlist organized by CED units. What I had mentioned are these Maxwell-Boltzmann distribution curves. So on the left, you can see what's happening as I raise the temperature. So as the temperature of the sample increases, you can see how that curve gets broader and flatter. The average kinetic energy of the particles increases as the higher temperature. The Maxwell-Boltzmann distribution curve becomes broader and flatter. And now look on the right side of this slide. You can see what's happening here is that we have a greater fraction of collisions beyond the activation energy. So at a higher temperature, a greater fraction of the collisions between the reactant particles will have enough energy to overcome the activation energy barrier. So explain how a higher temperature affects the collisions between the reactant particles. We have lower temperature on the left, higher temperature on the right. Higher temperature, higher average kinetic energy for the reactant particles, and therefore a greater fraction of the collisions have enough energy to overcome the activation energy barrier. Now, back to the curve that you're going to draw, it should be looking like the curve on the left. The peak should be a little bit higher and moved further to the left, and there should be a smaller area under the curve beyond the activation energy. So the dashed line, this is the answer that they were looking for on the AP Chemistry exam. The graph shows a distribution for collision energies at 120, that's the solid line. You had to draw a curve for 30 degrees Celsius. So one thing they were looking for is a peak that is located above and to the left of the given curve. That's the lower temperature. And then you had to show that the curve is below the given curve in that region beyond the activation energy right there. Now, what did students do potentially incorrectly with drawing that curve? Well, they should have drawn a curve that had a peak above and to the left of the 120 degree curve, and it should have been below the 120 degree curve in that region beyond the activation energy. So most students simply lowered the entire curve, maintaining the shape. So that was incorrect. They might have earned only 1 out of 2 points for that curve. Some kept the initial curve at the same height. They actually tried to change the position of the activation energy line, which is incorrect. But too many of the students simply merged the curves so that they were on top of each other at the activation energy line, or they drove the line below the x-axis, not really understanding that the area under the curve should be the same, so not really understanding how a Maxwell-Boltzmann distribution curve is affected by a change in temperature. So once the lower temperature curve drops below the original curve, it must stay below. So that's the intended answer, that the peak should be, for 30 degrees, above and to the left, and that below the given curve in that region beyond the activation energy. So that was the intended answer. So again, this was one of the essential knowledge statements for topic 5.5. The Maxwell-Boltzmann distribution curve describes the distribution of particle energies, and it gives a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction. So lower temperature, a smaller fraction of the particles have the required activation energy. All right, now let's go ahead and take a look at the next question in the packet. This is question 8. In question 8, it says, which of the following provides the most accurate explanation for the fact that an increase in temperature causes the reaction rate to increase? So the two factors that we have to consider here in question 8 are the collisions between reactant particles and the activation energy for the reaction. So how would those properties be affected by an increase in temperature? You may recall back in question 6, when we went from trial 1 to trial 3, we increased the temperature. And I said the particles at that higher temperature have a greater average kinetic energy, so traveling at a faster speed, colliding more often and with more force and more energy. But the activation energy for the reaction remains the same because there was no mention of a catalyst or an alternate pathway with a lower activation energy. So now back to question 8. Higher temperature, greater average kinetic energy, but the activation energy for the reaction remains the same. So the correct answer to question 8 would be choice D. Now, another question that I found related to this topic, this was from 2014. And so the AP Chemistry Free Response questions from 2014, I looked at question 7, part D. So in this question, they talked about the half-life of the reaction in trial 4 being less than the half-life of the reaction in trial 1. And it says, explain why in terms of activation energy. So if I zoom in on trials 1 and 4, we see same initial pressure, which means basically same concentration of the reactant, same volume, but the half-life was affected by an increase in temperature. So what did students have to do on the 2014 AP Chemistry exam to answer question 7, part D? Well, part D is essentially asking the student to explain why the reaction rate in trial 4, which occurred at 365 Kelvin, is a faster reaction rate than trial 1, which was at 350 Kelvin. Now, the student's response should talk about higher temperature. They should mention the activation energy for the reaction and somehow describe the average kinetic energy of the particles. So hopefully you can say something about kinetic energy, activation energy at this higher temperature. So this was the official answer from the 2014 AP Chemistry exam, question 7, part D. And again, I will put this information in the video description area for you so you can see that. The temperature at trial 4 is higher than the temperature at trial 1. Average kinetic energy of the molecules is greater. Greater fraction of the collisions have sufficient energy to overcome the activation energy barrier. So that's why the rate is greater. Higher kinetic energy and a greater fraction of the particles have enough energy to overcome the activation energy barrier. So what did students do wrong? Instead of talking about the energy and the activation energy and the higher temperature, they failed to connect the macroscopic measurements, such as temperature and half-life, to the events occurring at the molecular level. So talking about the collision between the particles and the activation energy. Some students said something incorrect, such as the activation energy becomes lower as the temperature is increased, which is not true. They thought somehow that heat is behaving as a catalyst. That's not true. They talked about how there's more activation energy, so they possibly was confusing the thermal energy with the activation energy. They referred to something known as the Arrhenius equation, which is something I do in my video for topics 5.4 to 5.11. You can check that out. And sometimes what students do is they simply talk about this variable goes up and that variable goes up, but they're not really explaining why. So if you say higher temperature, faster rate, that's not really an explanation. That's just a more generalized reasoning that says, well, the reaction would always proceed at a faster rate at higher temperatures, or that there's more energy, but not really talking about the activation energy and the collisions between the particles. So hopefully you can find this advice helpful as you're preparing for the AP Chemistry exam. Now there's one more question in topic 5.5, and this has to do with the collisions and the orientation of the collisions. Let's go ahead and take a look at question 9. Question 9 says, a proposed mechanism for a chemical reaction is shown above. Each of the particulate diagrams shown below represents a collision between two particles. Now, which collision, diagram 1 or diagram 2, is more likely to result in a successful reaction? Justify your answer in terms of the mechanism shown. So here in question 9, we're not worried about temperature, we're not worried about kinetic energy or activation energy. What we are worried about is the orientation of the particles that are colliding together. So you can see in step 2 of this mechanism, we have O, or oxygen atom, colliding with N2O, a molecule of N2O, and you can see that the white circles in the diagram represent oxygen atoms, and the black circles in the diagram represent nitrogen atoms. So how should this particle of O collide with the particle of N2O to result in a successful reaction? So what I'm focusing on step 2 is the newly formed bond. A molecule of oxygen, O2, is formed, which means that there should be a new bond formed between two oxygen atoms. I need an atom of O to bond with another atom of O to create a molecule of O2. And so that means that this diagram, diagram 2, shows a white circle colliding with a white circle, which means that two atoms of oxygen would collide together, and that would potentially lead to a successful formation of a bond between the atoms of oxygen. So here's my answer to question 9. Again, it's not about the energy, it's about the new bond that's forming between the atoms of oxygen. I said diagram 2 is more likely to result in a successful reaction because the orientation of the colliding particles is more likely to result in the formation of a bond between the oxygen atoms. So that's why diagram 2 would be the more successful orientation of the particles as they collide. All right, that's going to be the end of the practice problems for topic 5.5. So now it's time to move on to the review for topic 5.6, reaction energy profile. Here are some essential knowledge statements from the AP Chemistry course and exam description. Elementary reactions typically involve the breaking of some bonds and the forming of new ones. The reaction coordinate is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. The energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. And the energy difference between the reactants and the transition state is the activation energy for the forward reaction. The rate of an elementary reaction is temperature dependent because the proportion of particle collisions that are energetic enough to reach the transition state varies with temperature. The Arrhenius equation relates the temperature dependence of the rate of an elementary reaction to the activation energy needed by molecular collisions to reach the transition state. Now again, in my video for topics 5.4 to 5.11, I do talk about the Arrhenius equation, so you can check out that video. And now let's move on to the practice for topic 5.6. This is question 10. In question 10, it says the reaction energy profiles for two different chemical reactions are shown below. And we can see on the x-axis in each diagram, it says reaction coordinate. That was mentioned in one of the essential knowledge statements for topic 5.6. The reaction coordinate is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. So the energy profile gives the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. So I will label each diagram with reactants, products, and transition state. So that would be reactants and the beginning of the reaction coordinate, so R for reactants, and then products at the end of the reaction coordinate, so P for products. And then where is the transition state? Well, the transition state would be this point of highest potential energy in this energy profile diagram. Now, it says that the energy difference between the reactants and the transition state is the activation energy for the forward reaction. So I'm going to go ahead and label the activation energy for diagram 1 and the activation energy for diagram 2. So from the reactants to the top of that diagram, the transition state. So that's my activation energy. Now I'm going to go ahead and officially answer part A of question 10. It says, in the space below, circle the correct choices to complete each statement regarding these two reaction energy profiles. The reaction represented by diagram 1 is classified as and it turns out it's going to be exothermic. So it's an exothermic reaction because the potential energy of the products is less than the potential energy of the reactants. So energy is released, it's exothermic, products less energy than the reactants in the diagram. Then the opposite would be true for diagram 2. Diagram 2 is classified as an endothermic reaction because now the potential energy of the products is greater than the potential energy of the reactants. So energy is released in diagram 1, exothermic. Energy is absorbed, diagram 2, endothermic. Now, if you're wondering, do we know enough about energy at this point? This is Unit 5 is all about kinetics and reaction rate. I will tell you, as a little preview of things to come, that if these energy diagrams don't quite make sense to you in terms of endothermic and exothermic, when we get to Unit 6, which is entitled Thermochemistry, topic 6.1 is entitled Endothermic and Exothermic Processes, and topic 6.2, Energy Diagrams. So a little preview of things to come in Unit 6. Now, the last part of this particular question, question 10, I've already done that. So it says, on each diagram, draw a vertical line with a double-headed arrow that indicates the magnitude of the activation energy for the forward reaction. So these blue arrows represent the activation energy for each diagram. All right, well, since question 10 was the last question in this packet, now it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. Now, my first piece of advice is that if you need more practice problems or more information about topics 5.4 to 5.7, then you can review the information in my video for topics 5.4 to 5.11, and that link is listed here in the packet as well as in the video description area. My next piece of advice is what I normally say, and that is read the question carefully and make sure you are answering the question that's being asked. Now, my next piece of advice is that there is an important difference between the equation for an elementary step and the equation for the overall chemical reaction. So with an elementary step, that is a reaction that occurs in a single step. It's based on a single event or a collision between two particles, and the simultaneous collision of 3 or more particles is a rare event and not likely to occur. So here are 3 examples of elementary steps in the table on this slide and the rate law for that elementary step. Let's count the particles. So I see 1 particle of N2O5, so the rate law would be first order with respect to N2O5. So rate equals K times the concentration of N2O5. So 1 particle, first order. Now, the next elementary step, I see 2 particles of NO colliding together in that elementary step. So because there are 2 particles of NO colliding, then that rate law would indicate second order with respect to NO. So 2 particles, second order. And then our next elementary step, there's 1 particle of Cl colliding with 1 particle of O3. So the rate law would be first order with respect to Cl and first order with respect to O3 because there's 1 particle of each. Now, my next piece of advice is that if you are given a proposed reaction mechanism, make sure that you understand the difference between a catalyst and an intermediate. So a catalyst is a substance that is consumed in step 1 of the mechanism and then is regenerated in a later step of the mechanism. Whereas an intermediate is a substance that is produced in one step and then is consumed in a later step of the mechanism. And with respect to colliding particles, in addition to energy, if you need to choose a collision in which the colliding particles have the proper orientation that will lead to the formation of the products, focus on the chemical bonds that are broken and the new chemical bonds that are formed. And with respect to things such as activation energy and kinetic energy, if you increase the concentration of a reactant, but the temperature remains constant, this is what will happen. The frequency of the collisions between the reactant particles will increase, but the average speed and the average kinetic energy of the particles remains the same because the temperature remains constant. The value of the rate constant K remains the same because the temperature remains constant, and the activation energy remains the same. We will see in a future lesson that the activation energy could change, but in the presence of a catalyst. And we're not there yet, so activation energy remains the same because we're not talking about a catalyst, at least not yet. Well, what if instead of just increasing the concentration of a reactant at constant temperature, suppose you increase the temperature of the reaction? What will happen? The frequency of the collisions between the reactant particles will increase. The average speed and the average kinetic energy of the particles will increase because the temperature is increased. A greater fraction of the collisions will have enough energy to overcome the activation energy barrier. The value of the rate constant K will increase because the value of K is temperature dependent, but again, the activation energy remains the same. Okay, so we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 5.8 to 5.11. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.